Imagine you sprain your wrist. You try to write postcards, but it hurts to hold a pen. You want to send a personal letter to someone you love, but it's hard to form the letters on the page. You resign yourself to a life where all writing is done with printers. But what's this? Can it be? A device that handwrites for you? Introducing the Handwriting Secretary, our project for ECE453. This clever little bot listens to your dictation and writes whatever you want. No more frustrating Christmas cards for you. Handwriting Secretary is here to save the day.
Some major subcomponents of the physical plotter are the wood platform, the steel guide rods, the linear slides that move along the rods, the standoffs to hold the rods in place, the motors and gears to move the belts, the belt clamps, and 3D printed parts to connect everything together, hold the pen to the motor, and provide a standoff for the gear opposite the motor side. Mac decided to reinforce the 3D printed gear mounts with metals that they would hold stiff when the motor moves the slides. He also designed a pen mount to accommodate different sized pens. For PCBs, we designed a larger board that had 3 motor drivers on it. We also designed 2 smaller boards for debugging and testing. One of these boards was a power distribution board with pinouts that would allow us to drive up to 3 motors. The other small board was used to debug and test the motor driver ICs themselves. We used the DE1 SoC to drive direction and step waveforms to the motor driver boards and to run our speech-to-text conversion software. We ran into issues where the large PCB would not step the motor that we hooked up to it. We think this might be due to a power distribution issue. The gear mount standoffs went through a few iterations of designs. The first iteration would bend when we stepped the motor. The second iteration was supposed to be stiffer, but instead snapped when we put pressure on the standoff. The current iteration has metal screws as a spine or shaft that provides stiffness. We had issues with the smaller motor driver IC boards where our ground connections would come loose and it wouldn't be able to step the motor. We noticed that if we had a longer ground wire, the motor would not properly ground. We also had issues with these boards where the terminal connector would break and we would have to solder wires to the board to connect the motor.
Our software consisted of multiple stages and threads to convert audio input into signals to drive the motor. At the start of the chain was our speech-to-text conversion, done via Google's cloud service. We chose a cloud service to give us better comprehension, as Google would let us know what their final, most accurate result was. Then we checked for key phrases, and once the key phrase "Secretary Start" was spoken, the program would record every word into a buffer until the key phrase "Secretary Stop." On a separate thread, the buffered output would be written to a file. Around 30 characters of text would be added, which would be one line on our sheet of paper. We then utilized a third-party G-code converter to convert this text into G-code, and then passed it to a G-code parser written in C to convert each G-code command into the step and direction counts and pass that off to an FPGA. In the FPGA, we output a 50-50 duty cycle square wave for each motor. The period is software determined, as we also calculated the x to y step ratio so that we could modify the wave period for each motor, allowing us to step at any angle. Our device will listen to the user until they say, "Secretary, start." Then, text is buffered and sent to be converted. Text is recorded while the motors move, until "Secretary, stop" is said. Then, the remaining text will be written out.
As we've discussed, a variety of components went into the project's success. Creating these components, writing the software to control them, and combining these disparate pieces into a working whole was quite a challenge. In the end, I think we learned that 1. It's good to get ahead. At the project demo, all of us could easily see some simple fixes that, if we had started earlier, would have vastly improved the result. 2. Test everything. If not for Nolan's test boards, we might have spent countless hours trying to debug the large PCB with neither the knowledge nor backup solution those boards provided. 3. Divide and conquer. Breaking up responsibilities so each team member could focus on doing one thing well led to higher quality hardware and software across the board. And finally, always have spares. The number of boards used and the number of boards soldered aren't the same order of magnitude. In conclusion, this project was a challenging, educational, and above all, interesting experience. Thank you for your time and have a terrific holiday season.